a lot of what we did in 16.3 was for 2D vector fields, right? Which are conservative. So well, the plan today is how can I determine if a 3D vector field is conservative? To do that, we're gonna define two new tools. Okay. You guys think back of calculus. You guys used functions, right? And then you learned the derivative of a function, which gave you the rate of change of a function. How are the output values changing? So what we're going to do is we're going to talk about the derivatives of a vector field, right? We want to understand the rate of change within a vector field. And so there's two kinds of rates of change. And so that's what this little movie is going to be about. So let me pull it up. If you are familiar with a YouTuber that goes under 3 Blue, 1 Brown, they have really amazing videos. So let's take a look. And hold on, I gotta make sure I share it with sound. Here we go. Okay.
Today, you and I are going to get into divergence and curl. To make sure we're all on the same page, let's begin by talking about vector fields. Essentially, a vector field is what you get if you associate each point in space with a vector, some magnitude and direction. Maybe those vectors represent the velocities of particles of fluid at each point in space, or maybe they represent the force of gravity at many different points in space, or maybe a magnetic field strength. Quick note on drawing these, often if you were to draw the vectors to scale, the longer ones end up just cluttering up the whole thing. So it's common to basically lie a little and artificially shorten ones that are too long, maybe using color to give some vague sense of length. Now in principle, vector fields in physics might change over time. In almost all real-world fluid flow, the velocities of particles in a given region of space will change over time in response to the surrounding context. Wind is not a constant, it comes in gusts. An electric field changes as the charged particles characterizing it move around. But here, we'll just be looking at static vector fields, which maybe you think of as describing a steady-state system. Also, while such vectors could in principle be three-dimensional, or even higher, we're just going to be looking at 2 dimensions. An important idea, which regularly goes unsaid, is that you can often understand a vector field which represents one physical phenomenon better by imagining what if it represented a different physical phenomenon? What if these vectors describing gravitational force instead defined a fluid flow? What would that flow look like? And what can the properties of that flow tell us about the original gravitational force? And what if the vectors defining a fluid flow were thought of as describing the downhill direction of a certain hill? Does such a hill even exist? And if so, what does it tell us about the original flow? These sorts of questions can be surprisingly helpful. For example, the ideas of divergence and curl are particularly viscerally understood when the vector field is thought of as representing fluid flow, even if the field you're looking at is really meant to describe something else, like an electric field. Here, take a look at this vector field, and think of each vector as describing the velocity of a fluid at that point. Notice that when you do this, that fluid behaves in a very strange, non-physical way. Around some points, like these ones, the fluid seems to just spring into existence from nothingness, as if there's some kind of source there. Some other points act more like sinks, where the fluid seems to disappear into nothingness. The divergence of a vector field at a particular point of the plane tells you how much this imagined fluid tends to flow out of or into small regions near it. For example, the divergence of our vector field, evaluated at all of those points that act like sources, will give a positive number. And it doesn't just have to be that all of the fluid is flowing away from that point. The divergence would also be positive if it was just that the fluid coming into it from one direction was slower than the flow coming out of it in another direction, since that would still insinuate a certain spontaneous generation. Now on the flip side, if in a small region around a point there seems to be more fluid flowing into it than out of it, the divergence at that point would be a negative number. Remember, this vector field is really a function that takes in 2-dimensional inputs and spits out 2-dimensional outputs. The divergence of that vector field gives you a new function, one that takes in a single 2D point as its input, but its output depends on the behavior of the field in a small neighborhood around that point. In this way, it's analogous to a derivative, and that output is just a single number, measuring how much that point acts as a source or a sink. I'm purposefully delaying discussion of computations here. The understanding for what it represents is more important. Notice, this means that for an actual physical fluid, like water, rather than some imagined one used to illustrate an arbitrary vector field, then if that fluid is incompressible, the velocity vector field must have a divergence of 0 everywhere. That's an important constraint on what kinds of vector fields could solve real-world fluid flow problems. For the curl at a given point, you also think about the fluid flow around it, but this time, you ask how much that fluid tends to rotate around the point. As in, if you were to drop a twig in the fluid at that point, somehow fixing its center in place, would it tend to spin around? Regions where that rotation is clockwise are said to have positive curl, and regions where it's counterclockwise have negative curl. And it doesn't have to be that all of the vectors around the input are pointing counterclockwise or all of them are pointing clockwise. A point inside a region like this one, for example, would also have non-zero.
All right, hold on. Let me go back to it. So, so what we're gonna do is the way this is defined curl is kind of like a number. Okay. But the way we're actually gonna define it is as a vector. The curl will actually be a vector. So you're gonna get a point. You're gonna plug it into this thing called a curl, which is gonna produce a vector. And what that vector is gonna do is that vector represents the axis of rotation of that fluid flow. So if I plug in a point here, then it's going to give me a vector. It shoots out this way, and that acts as an axis of rotation. The longer the magnitude of that vector, the more rotation that's flowing around it. The smaller, there's less rotation. And if that vector is actually a zero vector, there is no rotation happening. So just keep that in mind. Right here, he's defining it as a scalar, but we're actually going to define the curl as a vector. Okay?
Spin around. Regions where that rotation is clockwise are said to have positive curl, and regions where it's counterclockwise have negative curl. And it doesn't have to be that all of the vectors around the input are pointing counterclockwise or all of them are pointing clockwise. A point inside a region like this one, for example, would also have non-zero curl, since the flow is slow at the bottom, but quick up top, resulting in a net clockwise influence. And really, true proper curl is a three-dimensional idea, one where you associate each point in 3D space with a new vector characterizing the rotation around that point according to a certain right-hand rule. And I have plenty of content from my time at Khan Academy describing this in more detail if you want. But for our main purpose, I'll just be referring to the two-dimensional variant of curl, which associates each point in 2D space with a single number rather than a new vector. As I said, even though these intuitions are given in the context of fluid flow, both of these ideas are significant for other sorts of vector fields. One very important example is how electricity and magnetism are described by 4 special equations. These are known as Maxwell's equations.
Okay, I'm gonna stop that. There's more to it, okay? I'll post it on Canvas if you want to watch more of it. Okay, so that's the theme of what we're going to do today. Okay, and this curl thing that was mentioned is the tool we're going to use to see if a vector field is conservative or not. Okay? Makes out of this. Three blue, 1 black. Amazing, beautiful, flawless, smooth videos every time. All right, so let me stop sharing. All right, guys. So that was the warm-up for today. We just kind of gave an idea of what we're going to do. So let's actually get on into it. Let's see how we're going to do this. Section 16.5, 4, and okay. All right, so let's start by continuing the story that we were doing on Tuesday. And so in section 16.3, we learned that for a two-dimensional vector field, let's say f contains functions p of xy, p of xy. It is defined, this is the new thing here, open, simply connected, that's in the notes, with many examples. Region, B, so this is one of the conditions, where P and Q have continuous partials. That was one of the theorems. I guess it was one of the bigger theorems we learned. Then there was a way to check to see if the vector field was conservative. You take the partial derivative of the x function, or p, with respect to y, and if it equaled the partial derivative of q with respect to x, that was equivalent to saying that f is conservative. That was part of what we did Tuesday, the second half of class. What did this mean, guys? F is conservative. Because there is a potential function. This means there is a potential function f, right? Some scalar function f, where the gradient of it is actually equal to that vector field. It is this vector, the gradient. Okay, that's what that is. So that was kind of half of what we were doing on Tuesday. And then we did a bunch of examples, we kind of played around with the theorem. So now the question is, how can I do this for a three-dimensional vector field? How can I check this? So to do that, we're going to need to define this curl thing. We're going to get two things first. So one, we're going to, there's this symbol here, right? When you guys see this symbol next to the little f, what does your brain do? What do you know you have to do after that? When you guys first learned the gradient, right? So what did you do to f? Took partials, made it into a vector, right? So that right there, that your brain doing that, that's what's called an operation. It makes you do something to the function. So that's called in math. That's called an operator, right? So instead of this, what if you saw this next to f? Your brain says just take the derivative, right? It's a function of one variable. So this right here is also called an operator in math, because it makes you do something to a function. Okay? So we're going to define this symbol, but now we're going to define it as an operator. We're going to say let del, I believe that this guy here is called del, be an operator where for this section it's going to be three-dimensional. Well, we're going to say del is the operator that takes the partial derivative with respect to x of something in the first component, takes the partial derivative with respect to y of something in the second component, and then with respect to z in the third component. For a two-dimensional version, it's just that. Okay? And so what this is going to do, think of it as think of it as a function. It's not really a function. But think of it as a function that inputs functions and outputs vector. No, outputs. How do I want to say this? Some type of derivative for that function. Okay? You'll see. I'm going to use it several times today, that way you can kind of see what I mean. Okay. So let me give you an example. If you have a function of, if you apply this operator to a function of 3 variables, I want you guys to think, we're thinking of this as like this kind of weird vector operator. I want you to think of scalar multiplication. Think of it like this. It's this vector here. Which is an operator, and you're doing like a scalar multiplication to f. Just the way with a scalar, right? You kind of distribute to each of the components. You distribute it into the first one, so you get this guy here. You distribute it into the second one, so then you get this partial here. And then you distribute it into the third one, which gives you this partial here. So it's the definition that we've learned for gradient. So kind of, you guys kind of see that? We just defined it this way, but here I want you guys to think of the operator is kind of doing a scalar multiplication to this function, so that you produce this new type of derivative. Okay. So the curl is gonna do something different, and it's not gonna do it to a scalar function. It's gonna do it to a vector. So this is how we're gonna define the curl. If you have a 3-dimensional vector field where you have P of x, y, z, Q of x, y, z, and R of x, y, z. Let me slow down there. So x, y, z's. So this guy here is defined and its partials, and the partials of P, Q, and R exist, then the curl of the vector field is going to be defined like this. You write the curl of f is the operator del using cross product of the vector field. And so what does that mean? Think of it like what we learned about cross product. I got this vector here, but this time it's an operator vector. And I'm crossing it with P, Q, and R. when you take the cross product of that, if I put P, Q, and R below it, now remind you cross product, you remove the first column, and then you do the product of this diagonal minus the product of this diagonal. But here the product really means this operator operating on R. So it's the partial of R. It's the partial of R with respect to Y minus the partial of Q with respect to Z. And then for the middle one, you cross it off, but remember you're going to negate it. You cross off the middle guy. So it's going to be the partial of R with respect to X minus the partial of P with respect to Z. And then for the third one, you cross off the third column, and then you do the partial of Q with respect to X minus the partial of P with respect to Y. And so then we get that the curl of the vector field is going to be partial R with respect to Y minus partial Q with respect to Z. And then here I distribute that negative, so then I just rearrange it so that this is going to be positive. Partial of P with respect to Z minus partial of R with respect to X. And then partial of Q with respect to X minus partial of P with respect to Y. And that's how we're going to define the curl. Notice it's a vector. It's a little complicated. We're getting higher level in math, so things are going to start looking funky like that. Whew. Crazy. So let me have you guys practice this. I'll call it example/practice. Just practice doing this here. So find the curl. Find the curl of the vector field xz, xyz, and then minus y squared. So practice doing that real quick.
Could you visualize the curve like an example to visualize it?
Yep, I'm going to show you all that in a little bit. Right now, I just want you to do a computation, and then we'll talk about like what does it represent. Yeah. Right now, there's a lot of computation to get to it, so I want to focus on that part. You guys as usual. I'm bringing Young Yang to the club. Be careful with all the partials here. A lot of room for mistake. Simplify your answer as well, please. right, when you get a chance, just check with your classmates. Just do a quick little glance, compare your answers, or compare your work. I want you guys to determine if your answer is a scalar function, a vector function, or a vector field. Okay, is your answer a scalar function, a vector function, or a vector field?
Here's no, it's not I see. I guess it's just a constant, so that's it. This one is here.
I just got YZ. It should be YZ minus 3.
And then don't forget the partial.
There's one curl just by so my final answer where the PQR is that vector is PQR.
Oh, yeah, that's these guys right here. So this is your P, this is your Q, and this is your R.
But then you're also taking partials of those same.
Correct.
PQ is just a position to mark X, Y, Z.
Oh, when find the cross product and we did the middle term, it always alternated between positive and negative. So that's what that negative. Yes.
So for the vector that you're crossing with the PQR, y squared.
All right. Hopefully you got something like this, guys. This one here, first one, you take the partial of R with respect to Y. That's going to be minus 2Y. Minus the partial of Q with respect to Z. So X and Y are constants, so it's just going to be the constant. And then for for the middle term, you're going to get partial of P with respect to Z. So that should just be X. Minus the partial of R with respect to X. There's no X, so that's just a constant. So that would be 0. So this is like X minus 0 here. So it's just X. And you get the partial of Q with respect to X. So here Y and Z are the constants, so the derivative is just a constant. And then minus the partial of P with respect to Y, there's no Y there, so that's just a fat constant. So that's like YZ minus 0. So there's like 2 of you guys that were wondering where this minus came from. Remember that when we defined the cross product, it alternated sign. It was it went from positive, negative, positive. So that's where that came from. It was from the definition of a cross product. Okay. Is this answer a scalar function, a vector function, or a vector field? So to answer that question, you guys have to remember, what am I inputting and what am I outputting? So what are you inputting to this result? Oh, I'm glad I asked that question. Okay. Let's go to this one. What do you input for this one? You input a 3-dimensional point, right? So here, you're going to input a 3-dimensional point. Okay? Here's my green marker. So in reality, what this really should look like is like this. The curl of f x, y, z. Like that. Because it's really a vector field. Okay? So this still will input a point, x, y, z, and then it'll still output a vector in 3 components, which is this guy here, a 3-dimensional vector. Okay. But here's the question now is, let's say I plugged in a point to this guy. Someone give me a random 3-dimensional point. 304, that's what I heard. Okay? So that means that when we plug in this point to this new vector field, just the way in calculus, you guys had a function, you took the derivative itself was a function, right? That you plug things into, and it gave you a rate of change and all that stuff. So here, you're gonna get a point that you plug into the curl vector field, and let's see what we get. So -2 times y, that's 0, minus x times y, that's 0. And then, so that's just a fat 0. And then you're gonna get comma, what is that? 3?
Yeah.
Just x, right? So just 3. And then y times 0. So that's just 0. Okay. So now the question is, what the hell does that mean? Like, what does that vector represent? Okay. So if you guys open your image packet that I gave you guys, the chapter 16 packet, and you open up to section 16.5, it's going to answer that question. So question, what exactly does the curl of f represent? And then how is it related to the original vector field? How is it related to the vector field? What does this vector here really mean? So here's my answer. I've run out of space. So given the vector field f, on that handout that I gave you, you'll see that it says vectors near a point x, y, z tend to rotate, tend to rotate, will rotate about the axis of rotation, which is the vector that you get when you plug in that point into the curl. So there's this vector field, right? And it has all these different vectors flowing. But at the point 304 in space, it's telling you that this vector here, okay, let's see if we can draw it. We've been practicing drawing so much that maybe we can do it. Let's see, we got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So you got this point, let's see, let's plot that point, 304. So that's 1, 2, 3, y is 0, and then it goes up 4 units. 1, 2, 3, 4. So here's the point. Okay? From that point, we can sketch this vector. It does not increase in the x direction. It increases 3 units in the y direction, but it doesn't increase anything in the z direction, right? So notice that this vector is going to look like this. 1, 2, 3. Like that. So I can't graph the vector field, but that means that when the vectors are around this point 304, they're going to rotate using the right-hand rule with respect to this vector. So they're going to be going like this, and that's going to act as the axis of rotation. So I have a little picture here. So it'll look kind of like, oh no, what happened? Uh-oh. Dang it. Sorry, hold on. Stick with this. Hold on, hopefully it connects. Okay, so it acts like this, right? But it's just flat, which is hard to see, but the vectors are going to be rotating, so there's a bunch of little vectors that are going to be moving in this direction like that. Or, as they showed in the video, there can be stronger vectors going this way and vectors going in this direction that are not as strong, so that there's still some kind of rotation, like the way they were showing in the video. If there was a twig here, the fact that this is going faster would make it rotate this way like that. Right, so that's kind of what's happening. It's helping you understand the flow at this point and how things are rotating, how the flow is rotating about that. That's what's happening. It's a little hard to visualize in 2D, and I definitely don't want to do it on graph in 3D because there's just so many vectors. It's hard to see. All right, so we have questions. Yeah.
What about how, like, the right hand rule shows the description?
Let's see. So I guess if we our thumb, if we point our thumb towards that vector, this would be going this way, and this would be going this way towards us, I guess. Yeah, it'd be kind of like that. So it's like it has to go through this direction first, and then this direction next. So that's what makes it this way. This is if the vector was going in this direction, if the vector would go here first, and then you can make it better. Is that cool? Kind of? Still kind of crazy, right? I'm not gonna have you guys graph or anything like that, okay? I just want you guys to kind of get a feeling for what this thing is. Right? Bonus bonus point if you can draw the vector field in the flow of rotation. That'd be good. The other thing I wanted to mention that was kind of mentioned in the video is the magnitude, which is also in your packet, the magnitude of the curl vector that you get when you plug in a point measures how fast the vectors of f rotate. How fast they rotate. Is there a lot of rotation happening, or is it very small amount? And then the last thing, which is the important part that we're going to use for the theorem, if you plug in a point, and you end up getting the zero vector. We were very close to getting the zero vector from this one. We get the zero vector, then there is no rotation at that point, and f is called irrotational at that point. So that's all in the packet that I need. If you want to write it down, it's up to you. And then the little visual, but that one I just projected it. It'll be there in the notes, so the little rotation picture there. Okay, so any other questions on the definition? So I want you to see that it's a vector field, and I want you to understand what the vector's output. Okay? So here's our first theorem for this section. We have that if F is a three-dimensional vector field. Oh shit, no, I'm getting ahead of myself. Sorry. If little f is a function of three variables, that has continuous second order partials, you guys learned the theorem in chapter 14 about a function that has continuous second order partials. And it starts with a C, the name of the theorem. What is it? Clairaut's theorem. Remember that meant that the second partial derivatives were equal to each other. Okay. There's a similar version for Clairaut's theorem for a function of three variables. Okay. I'm going to show you a little tiny proof of it, so you understand the next part. So if this is true, then when you take the curl of its gradient vector field, it will always be zero, regardless of the points that you put it. That means that if you take the gradient and you do what you guys did here for this practice problem, it turns out everything cancels off, and you'll always get 0, 0, 0. Yep, and let me show you why. So if I have the gradient, which is partial of x, partial of y, partial of z, right? That's the gradient vector field. This is like the p, this is like the q, this is like the r. So when you take the curl of this, you're going to take the partial of r with respect to y. So then that's where you get the partial of z first, and then the partial of y second. Okay? You're taking the partial of r with respect to y. That's what you get. This minus the partial of q with respect to z. So that's why you take the partial of y first, and then you take the partial of z second. So basically you do that the way you guys did it for the curl of like this one, and you end up with this result. Okay? Then by Clairaut's theorem, these two are equal to themselves because they're just the alternate versions of the second partial. These two are equal to themselves. These two are equal to themselves. And so everything cancels off. And so that's where you end up with the 0 one. Okay? And that means that any point that you plug into the curl of a gradient vector field, you're going to get, you're always going to get the 0 vector. Always. So what does that tell you? What does that tell us? Can I have you guys discuss with your group? What does that tell you about how the flow of a gradient vector field behaves? Let me have you guys discuss that with your group. Okay? Think about it. See if you guys can put your brains together. How does the so how does the flow / rotational flow behave for a gradient vector? That's the question.
Just another thing else.
The gradient is a vector field, right? So it has all these vectors in it. They're taking the fluid flow here. There's like fluid moving in the directions of them. In this one, we saw that at this point, for example, there has to be some kind of rotation happening about that point. Okay? But with this, for a gradient vector field, that's what this theorem says, the curl will always be the zero vector, regardless of the point. The theorem says that also for the gradient vector. Yeah, that was accurate. Because it counts. Yeah, because it starts here and then it will this is like which is the vector. Okay, guys, share with me what you said. Kirill, what did you guys talk about? Any ideas?
You said the derivative of constant would be zero. You would not increase
The curl would not increase or decrease. Okay. Forever or just at specific points? Just at specific points. Okay. So there is no increase or decrease. Okay. Like that. Let's see, Jacob. What did you guys say? Thank you. What's the flow?
Yeah.
Would be the same. Okay. All right. So let's see. So I have the rate doesn't increase or decrease, and then you're saying that any given point. What did you say? Okay. Okay. All right. So at any given point, the rotation, is there rotation or is there's no rotation? Okay. All right. All right. Anybody want to add to that in your discussion?
The flow just go past it and no rotation.
And there's no rotation.
Yeah.
Okay.
And I guess maybe it's conservative.
Well, that's kind of where we're going. That's kind of where we're going. So for example, if there was a point in space, would it be possible for some vectors above it, whatever that means? Because it could be like that, right? But it makes sense for vectors up here to be bigger than the vectors in the bottom. No, right? Because then if I do that, if I put a little twig here, think of fluid again, this means that the stream is going faster above it and slower below it. So it would force the twig to spin. So then there would be rotation. So there should be a vector that acts as the axis of rotation. But this is saying that it'll always be the zero vector, right? So it's not so much that there is no rate of change. It just means that it would be equally rotating, so that the twig would be being pushed this way as just as much as it will be pushed up here. Okay, yeah, Ben.
Won't they have to be pushed in the same direction because you would spin this way? Because if it's being pushed on opposite ends.
Oh, let's see. You're right. Yeah, you're right. Mm-hmm. So I guess it's more than just rotation. It also maybe is telling you that there is no opposite type of flow. kind of like the picture that the video showed with the circle, with the fluid all going in one direction. Okay? Okay, sweet. So if this is true for all gradient vector fields. Okay? So if it's true for all gradient vector fields, then what if this vector field, actually let me say it this way. Yeah, this is more fun. Is this vector field conservative? Using this theorem. Let's say it was conservative. Right? If it was conservative, then that vector field should equal the gradient of a function, right? But if it equaled the gradient of a function, this theorem says that when you computed the curl, it should have equaled 0, 0, 0, and it didn't. So it can't be conservative. You see kind of how that's getting us to like what we want? Okay, so that takes us to our second theorem. I know, so many theorems. I'm sorry, guys. So this is the one that's going to look similar to what we did in 16.3. So if f has 3 component functions, is defined on an open, simply connected region where the 3 component functions PQR have continuous partials, then if the curl is equal to the 0 vector, that is a criteria that will tell us if the vector field is conservative. I'll share my screen. Oh shit. A little bit more straight. So that's the one we're going to use. Okay, so this is kind of similar to what we did in section 16.3. You want to check that you have an open, simply connected region. For example, this guy here. Do these functions have any restrictions for the points x, y, z?
No.
No, right? So what's the domain of this vector field?
R2.
All of R3. Any three-dimensional point could be plugged in, right? So all of R3 is open. There is no boundary to it, right? There's nothing that bounds R3. It is one connected piece space. It's not disconnected. And there are no holes in all of R3. So it's defined in an open, simply connected region. It's polynomials, so they all have continuous partials. And the curl did not equal 0. So it's not going to be conservative. Okay? That means you cannot find a little function f so that when you take the gradient of it, it'll give you that. It's impossible. This is what this theorem is. Okay? And so some comments that you're going to want to use for your homework is the first one is R3 is open and simply connected. Most of your homework will have domains being open. And then number 2 is this theorem generalizes the theorem from section 16.3 that we learned on Tuesday. Let me show you what I mean by that. So in section 16.3, we said that if we had a two-dimensional vector field that was defined on an open, simply connected region, whose partials were continuous. Yeah. Open and simply connected. Remember, open meant no boundary. Connected means it wasn't disconnected into several parts. And simply meant there was no holes in that region. Oh shit. Simply, oh yeah, it does. Oops. Thank you. That's my brain. Simply connected. I did it where? Thank you. Thank you guys. Thank you. I'm saying it, I'm not writing it. Thank you. Okay. The theorem from 16.3 said, let's say that it's defined in an open, simply connected region. What did you guys do in 16.3 to see if this was conservative?
Also, Q based on X and also P goes to 1.
Yeah, you checked this guy here, right?
Yeah, it's if they're equal.
That's what you guys did in 16.3, right? So if you guys remember from chapter 12, you can turn a two-dimensional vector into a three-dimensional vector by letting the z component just be 0, right? So I can turn this vector field into a three-dimensional vector field where I still just let p be of x, y. You let q be of x, y, but you just let z be 0. Do the same thing, just let z be 0. Okay. All right, with this guy, help me take the curl of it. So r is 0 basically here, right? R is 0. So take the curl of that real quick. See what you get. Take the curl of this bad boy here, leaving it in terms of p and q still. Show me what you guys get. Well, right now it's conservative if this is true, right? But let's just pretend we don't know if that's true. This is a vector field, I'm turning it into a 3D vector field, and I'm gonna take the curl of it. But it should be. Let's see what happens. The curl. So you need to practice follow. R right now is just a 0 function. All right. Are you guys getting 0 for the first component? Getting 0 for the first component. What do you get for the second component? You should also get 0. Okay. And then for the third component, you would get partial of q with respect to x minus the partial of p with respect to y. Okay? What should happen so that this vector field is conservative? You want it to be 0, right? So if in order for this to be 0, what does this need to be?
0, 2.
So notice that for the curl of f to be the 0 vector, we need the partial of p with respect to y to be equal to the partial of q with respect to x. And so that's why that theorem uses this. Remember I was telling you guys it was a little bit mysterious why this is the criteria? It has to do with this. So that the curl is 0, so that we can guarantee there's no type of rotation happening. So I just wanted to show that because I promised you guys I would explain why this criteria was needed, and it has to do with the curl. All right, so that you guys practice something like your homework. I got 2 practice problems for you. So determine which vector field is conservative using a new little test here. So the first vector field is sine of yz, sine of xz, and then sine of xy. And then the second vector field is e to the yz, xz e to the yz, and then xy e to the yz. Practice that real quick. You're going to do this. You're going to need to know how to do this for later on when we bring in line and integrals again. Let's do this practice and then I'll take a break. Work with your groups to check. Not sure where to start. Remember, you gotta check the domains open simply connected, and then confirm the curl is in. Where'd you go? Here it is. Okay. In case you need to see the curl again. Oh, see, some people kind of going with it, and some people are still kind of staying. It's okay. Anybody guys just check in with your group real quick. Real quick check in, guys. Just real quick. We're talking about the domain. Line has the known that's the range.
I know there's it's also actually it doesn't matter. I don't it's gonna spit out where you want because it doesn't take
Yeah, order is.
Right.
it can be any number.
I guess the first one is in. It would be nice to the whole I got zero. Like every time you do, the first but they actually like that's classic. Like surgical. Yes. How three about like okay, the first one well you usually set a place where no come on. You know that. I used to have friends. I don't know. They're figuring out. I don't know. That happens.
So with the minus sign there, with the determinant, you could just do the like reverse determinant.
Exactly. Yeah. And that's what ends up happening here.
It's much easier, maybe just the linear algebra, it's much easier to understand with
The negative first? Yeah. That's usually how I do it. The book will just do it like that.
That's the last
Bridges that everything you said here is still true for the section. uses is this thing. The three-dimensional vector. So three-dimensional vector field is this. The three-dimensional vector field is this. All this is this was me explaining to you guys why this theorem has this connection. Because it's a little surprising that where this came from. I'm going to show you the possibility for the the curl of it. Remember the curl 0, 0, 0. These two which is why the two-dimensional field is that's how it is. In order for this theorem to be true, the reason this theorem has to be true is because this theorem and this theorem is true because we don't want any rotation because now we understand the curl and all right, guys, let's see. So for number one, did you get a zero vector field? No. You did not. You get, double check here. Help me out. What do you guys get? X cosine x1. X cosine y. xy, thank you. Minus dx, comma. Let's say you're working this out. Let's say it's on the homework or in the class, right? And you're working this out and you want to check if it's conservative. Immediately, do you know this is going to give you the zero vector? You could just stop right there and just say, oh, it's not conservative.
Oh, wait. No, it's smiley face.
Just because you know immediately it's not going to be the zero vector because that one didn't cancel out.
So all three positions should be zero.
All of them have to cancel out.
Yeah.
And in this case, I think, let me see, was this y cosine yz? Minus y cosine xy, and then z cosine xz?
Yeah.
Okay, and then z cosine zy. Hella not the zero vector. Okay? So, yeah, this definitely does not equal zero. What's the domain of the vector field? That's right. All these trig functions are defined everywhere. So the domains are 3. And so the theorem tells us this is not zero. So boom, f is not conservative.
What would be the next step in finding the curl?
You mean the next step after this conclusion?
Yeah. Did you have
to-
to plug
to-
in points? You had them?
Well, no. So all we're trying to see if it's conservative. If it's not conservative, remember that meant that there was no potential function. If it is conservative, the homework will say, then find the potential function, which is the next part after the break. Okay? All right, what'd you guys get for the curl of this bad boy? You did not get 0? Ah, let's do that together. Yay! Okay, let's see. P, Q, R, right? So it was the partial of R with respect to Y. So that's
X e to the y side.
oh, I think the product rule probably messed some of you guys up. You're doing it with respect to Y. This is a function of Y, and that's a function of Y. Am I recording?
Yeah. X to product.
So you're gonna have to do the product rule. Okay? So let's do the product rule. Let's do the partial of R with respect to Y. Take the derivative of this with respect to Y.
X e to the y side. Oh, no.
Plus
X, y,
and then the derivative of this with respect to Y, which uses the chain rule.
yeah.
So it's e to the yz
Times c.
times the derivative of this with respect to Y. That's the partial of R with the product rule. Okay? Because this is a function of y, and this is a function of y. So you take the derivative of this bad boy with respect to y, that's x, multiply the second function, plus the first function times the derivative of this with respect to y, but then you gotta use chain rule with the yz on top. So then you end up with x e to the yz plus xyz e to the yz minus the partial of, which one was it, q? Q with respect to z. So then, let's see. With respect to z, oh my gosh, another product rule. So you gotta do partial of q with respect to z. Again, let's do it, product rule. Take the derivative of the first one, what is it? X, bring the other function along, plus bring this guy along, z, and then you take the derivative of this with respect to z, that's 1. So then you're going to minus all that. So that's going to be x e to the yz minus, you distribute the negative, x, y, z, e to the yz. So you guys see how that's going to cancel out? This cancels off with this one. And this one is exactly this one. You get 0. Ooh, good times. All right, and then the second one, you do the partial of, what was it? Partial of, was it q, r? Let me see this. Partial of r, right? With respect to x. Yeah. Is that product rule?
Oh, yeah, you just have to make it negative.
Oh, thank God, it's not. Okay, it's just partial with respect to x. So all this is a constant. So it's e open y e to the yz minus partial of p with respect to z. So you got to do chain rule. E to the yz, take the derivative of the inside function with respect to z, multiply by y. So now these cancel. And then lastly, we got the partial of q with respect to x. Product rule? No, it's just x. So this is all a constant. So it's z e to the yz minus partial of p with respect to y. So it's going to be e to the yz times the derivative of the inside with respect to y plus z. Beautiful. Wow. There it is. Cancels off. Very time consuming, I know. So you do get the zero vector. That's what should happen if it's conservative. Okay? Everything will cancel out beautifully. Therefore, there's a lot of room for mistake. So you make one little mistake and then I won't tell you that it's conservative, but it really should be. Let's take a break though. Good. Take a break. We'll resume at let's see, 120, let's say 225. 225.
Is there like a handy way to check your work on that, or do you...
Okay. So what did we just do? Let's see. We found out how to see if a 3D vector field is conservative. So now the next natural piece is, if it is conservative, then how do we find the potential function? So let's use this bubble here. Very similar, yeah. So to find the potential function of a conservative vector field, we again, like we did Tuesday, use indefinite partial integration. And again, the book will do it different, but we're going to do it the way I showed on Tuesday. So let's use number 2 that you guys showed was conservative. So find the potential function at the vector field. Number 2, and let me just show this conservative. E to the 1z, x, z, e to the 1z. And then x, y, e to the 1z. So remember, this means, because it's conservative, that means this guy is supposed to equal the gradient of that potential function. Right? So this guy is equal to this one. This is the partial with respect to x. This is supposed to equal the partial with respect to y. And then this is supposed to equal the partial with respect to z. So we're going to do the same trick that we did last time. Find f. We're going to undo the partial with respect to x by integrating that partial of x off. So that means we're going to integrate e to the yz with respect to x. What is that going to give us? When you integrate with respect to x, e to the yz, x, e to the yz, plus a constant, right? But now you have 2 variables. So what the constants are y and z. So we're going to write, we have some expression, some function in terms of y and z. So instead of just 1 variable, this time it's 2. So this is a constant. And that expression, can it have any x's on it? No. It cannot have any x's. So what this will have is terms with y and z only, or a constant, like literally just a number, right? So it'll have terms that have y's and z's only, or just a constant. That's considered a constant when you integrate with respect to x. Keep that in mind. That's like our mu plus c. So then we did it for x. Now let's do it with respect to y. So if I want to find f, I'm going to undo the partial of y by integrating it with respect to y. But that partial is xz e to the yz with respect to y. Ooh, this one we got to be a little bit more careful. We could take out the xz, you're right, we could take out the xz, because that's just a constant. Like that. Those are just constants. So we got to do either a little bit of u sub. We won't take that route. So let's say we take u here. What is u going to be? Yz. So then you take the derivative both sides with respect to y. What's the derivative of that with respect to y? Z dy. Divide both sides by z. That. So then we get x, z is outside, and now you're going to integrate e to the u du. Oh, sorry. 1 over z du. Pull that out. When you pull that out, what happens with the z's? They cancel off. This guy cancels off with this z. What's the antiderivative of e to the u? It's e to the u. So it's x e to the u, bring back the u, yz, plus my constant. But what's my constant in this case? Things with x's and z's. So we're going to call that h. Things with x's and z's.
Can you take the natural logarithm of stuff inside the integral?
No, because you can't, like if I have the natural log of this, that is not equal to this. Yeah, you can't do it. Okay, and so remember, I'm just gonna write this. You don't have to write it if you don't want to, but these are only terms with x and z only, plus a or what did I say here, or a constant, or a constant. So then we got to do it now a third time for the z's. F, undo the partial with respect to z. Let's see if that gives us something new. So I'm going to integrate x, y, e to the yz with respect to z. So similar to the problem above, we could take out the x, y, because those are constants. Let's take out the x, y. And then we can literally do the same kind of u sub, because it's yz, right? So this itself, when we do the exact same u sub, we're going to get, wait, hold on, let me slow down. Hold on. If we do the u sub again, yeah, let me slow down. This time we're going to take the derivative of both sides with respect to z. So we get y dz, and then you get 1 over y du. So now which one cancels off? Now the y's are going to cancel off. Yeah. Yeah, so it's very similar to the top. The y's cancel off. And so, yeah, we're going to get x e to the u, which is yz, plus a constant third function. Let's use the letter p for that one. What are the variables that are constant? X and y. All right, so these are terms with x and y only, or constant. And a lot of you guys were asking me this next part at office hours. Let's chat about it. Okay, so now that you do all that work, then you have to figure out, okay, from that, how can I conclude my potential function f? So, since you know f has to be either of this form, or this form, you just pick one. You can start by just picking one, okay? So you put all this together, and then you say, okay, let's just pick one here. You guys want to pick the first, second, or third form? They look the same, right? So let's say I pick this one. We know this seems to agree with everything. This term has to be there, right? This term, I have to look at the other two and see, does this give me a term that with only x's and z's only? No. This one? No. So then the only thing this could be is a constant. So then I have no choice but to do that. It's just a constant. That's how you kind of want to work that out. If I would have started here, pick this one, I bring this guy along, and then I see, okay, does this have terms with only x's and y's? No, because this one has a z. Does this one have terms with only x's and y's? It does not. So then it just has to be a constant. Okay. Versus if like maybe this one randomly had like a xy squared, then when you get to the step, you would say, does this one only have terms with x's and y's? No. Does this one have terms with only x's and y's? Yes. So I bring that one along. And then it's plus my constant. Okay?
So they should always have at least one in common, right?
No. You can have a potential function, for example. Let's say the potential function looks like this. Right? This, you would get one of the integrals would give you this guy. One of the integrals would give you this one. And one of the integrals would give you this one. So the answer is no. You can get it so that none of them. The thing that they agree on, the thing that they will agree on is a term that uses all three variables. That's something that they'll all agree on. Okay. Let me remind you why the hell you care about this. Okay? Why do we care about finding this potential function? Okay? And let me remind you with the little concept map I gave you guys on Tuesday. Where is it? Let me see. Is it this one? 16.3. Hold on, give me a second. Oh, here it is. So I gave you guys a concept map that looked like this. Let me show you. You guys remember this one I gave you? If you weren't here Tuesday, these are all the theorems that we discussed. It was a hell of theorems. So, can you guys see that in the back? It's too small, the writing? Good? Okay. So the entire reason why we care about finding conservative vector fields is so that we can use this theorem, the fundamental theorem of line integrals. Okay? Because I can, instead of doing a line integral, I don't have to do a line integral. I just grab the endpoints of a curve, and then I plug in the endpoints to that potential function that we just found. I can avoid doing integration entirely. And I just find, I mean, not entirely, because we kind of did it here, but a line integral. You can avoid doing a line integral entirely and not have to do this part, and instead just get the potential function and then plug in the endpoints and integrate. Okay? If we have a curve, let's say that is a circle, okay? Let's say this is C, and I'm being asked, let's say I'm being told to find the line integral. I'm going to write it formally. Right now I'm just kind of saying it out loud. Let's say there's a 3D curve that is a circle floating in space like this. Let's say where z equals 1. It's a circle like that. Okay? This is my curve oriented this way. And I'm being asked to evaluate this three-dimensional line integral along this curve C that you did on the homework for 16.2. Okay? You would have to parameterize that curve, compose it inside the vector function like you did for 16.2. You'll have to do all that. Okay? But if I can, we just showed that this vector field is conservative. So because it's conservative, if I use the theorems I learned in 16.3, I know that for a conservative vector field, it's path independent, and the line integral has to equal 0 for any closed curve. Therefore, because this vector field is conservative, if I'm asked to compute the line integral along this closed curve, by those theorems, I don't have to do it. It just equals it. Because it's a closed curve. And my vector field is conservative. So that's how you would use this concept to avoid all that work. Okay? If it was not conservative, then I'm going to cry, because then I have to parameterize this with R, and then do everything you did for 16.2. Okay? If the curve is not closed, let's say it's a line segment from here to here, let's say this is the point 0, 0, 1, and this is the point 0, 1, 0, and I am asked to find this line integral. Well, I can either do the line integral and parameterize C, or because the vector field is conservative, it has a potential function, f, which is what we just found. And so therefore, this line integral, because it's conservative, it really equals the gradient of the function. So then all I really have to do is plug in the endpoints of my curve into that potential function that we just found here. So then I would just plug in the ending point, which is 0, 1, 0, minus the initial point, 0, 0, 1. Plug it into this guy here, and then I'm done. That's the entire, it's just been it's so long and so complicated. And this is why you guys are learning how to find conservative vector. It's really short. Huh? Questions?
We can just use the theorem of if like we found out it's a conservative.
Correct.
But SFF.
Correct. So yeah, I just wanted to kind of bring it back to the theorem that we discussed on Tuesday. And then it was very loaded with theorems. I'll move this way. I'm gonna have you guys do this instead. Okay, so I have a handout. Have I talked about this yet? No, I have not talked about this. Hold on. I need to go over one thing. Okay. So we talked about curl, conservative vector fields, and then there was this other thing called the divergence. Okay. Let me define that real quick, and then I'm gonna have us try some problems out. You guys practice your notation. This beautiful work. Scooching on here. It's the following divergence. Okay? Play around with this stuff, okay? Divergence. Yeah. Yeah. All right, so let's see. So this is a different kind of derivative of vector field, okay? We're going to have that. If you have a 3D vector field with P of x, y, z, Q of x, y, z, and R of x, y, z. Is a vector field where the partials of P field exist. Then the divergence of F, we're going to define it like this. And so the divergence of F So remember how we did del, and we did the vector field, when we defined the curl? At the beginning of the class? What was it that we couldn't do? What did we do with this del operator? We did the cross product, right? This time we're gonna do the dot product. It's gonna be okay. This is what's gonna happen. This vector, remember, we defined it to be a vector that contained the partial operators. And F is just the vector field with Q, and R. And so here it's kind of a little weird. But when I multiply P with the first component, remember when we do that product, it was the first component times the first component, second times the second, and then we added all those. But here, I'm not really multiplying it, I'm going to operate on P. So it's the partial of P with respect to X, plus the partial of Q with respect to Y, plus the partial of R with respect to Z. That's what we're going to call the divergence. So it's different. Is it going to give you a vector field? Like the curl did? It's going to be, there's no vector, right? It's going to be a scalar in this case. So let's see, let's grab the vector field we did in the beginning. It was xz, xyz, and then minus y squared. So this is like my p, this is like my q, and this is like my y. So the divergence of that vector field, let's see what we get. This was way easier to compute than the curl. We take a partial of p, and we a partial derivative with respect to x, what is that, z? Z plus, what's the partial of q with respect to y? Is it? xz, xz, and then what's the partial of r with respect to z? Just a big fat 0. So notice that this guy here is really a scalar function that plugs in 3-dimensional points, and it gives you the number, whatever this ends up giving you. So it's definitely not a vector field. It's going to give us a scalar function. So for example, if we plug in a point, let's say we plug in the point 0, 1, 0 versus plugging in the point 0, 0, 1. Plug in this point, let's see, x is 0, so that goes to 0, and z is 0, so everything is 0. And then for the second one, let's see, x is 0, so this guy's 0, z is 1, so you get that. Beautiful question. Yeah, so what the hell does that mean? Okay. Do you guys remember the video, and you think of the vector field as like a fluid flow, things moving? This is not measuring rotation at all. It's measuring like how much something flows through that point. So if you guys look at your packet, that for this chapter, let's see, where is it? Where'd it go? Hold on. Oh, is it down here? Oh, it's down here. Okay. You guys look at the packet here. You scroll down to the bottom. So this is divergence, okay? And so for divergence, if you plug in a point and you get a positive answer, what's happening is that, think of it as like you're getting a flow rate. The flow rate is going to be increasing. It's going to go faster. So it can start small and then it goes up faster. In the video, they were showing you kind of like a black hole or like a little funnel, where things were coming out of it. They're going slow and then they shot out of it. So it's like you're having something going through it slowly and then it goes faster. This is, if you plug in a point and you get a negative, think of it as like sinking. It's going fast and then it slows down and it goes into it. Or it's going fast and then it slows down as it approaches. Okay? Versus if your divergence is 0 at that point, there is no difference in the rate of how the vectors are flowing through it. That's what it's called. Compressible.
So that's the means like the vectors are all parallel, isn't it? Or just this.
It's telling you more about how things are flowing through that point. So it's telling you that, like for example, if you think of water, in this case, it's going towards it, right? But it doesn't always have to go towards it. It could just be flowing through it. But it's saying that the water would be going really fast, but as it approaches it, it slows down a lot. The net change of it, of all the vectors around it. That's kind of the type. Versus this one, the flow rate is slow, and then as it approaches it, it starts to increase. Or this one, there's the flow rate is there is no change in the rates. The water would be streaming the same, flowing through it at the same constant. That's kind of
So in principle, I should talk about is consider the same like the blending temperature and the air like temperature.
I don't know if it talks about it being perpendicular or not. It's more about motion, and how that rate of motion is flowing through that. And then usually, yeah, it's fluid or some kind of physical thing that helps to think about how that's happening. Luckily, there's no theorems we're going to learn about divergence, except at the very end of the semester. It's called the divergence theorem. But we'll put that, we're going to wait to 16.9 to do that. Okay. So, let me just write these notes down. And so what this is telling you is that the flow rate of F near that point, near the point 0, 1, 0, doesn't change, or it's constant. Well, this guy here is telling you that the flow rate of F near that point increases as it's increasing. Yeah.
In this context, what is near me? Because that's a relative term. So what is near?
Actually, let's change near. Let's change near because I do have a different one. So flow rate of F. Let me say it this way. Increases as it passes through that point. As it passes through that point. It's similar to approaching like in calculus, except that here as Ben was saying, like, what do you mean by approaching near what? So it's kind of like within a small distance of that point. The vector's going through it. And then you guys remember the video, it was like he was like moving the point and showing these vectors coming out of it and near.
And I realized like the flow rate is actually the velocity.
You can think of it like that. Someone else had it. Is that you know? Okay, guys. So I'm gonna make you get up because your energy is way too low. Okay. Let's see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, we'll give you a number, okay? 1, 2, 3, 4. 1, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then 1. All right, so if you're 1, go to this corner. If you're 2, go to that corner over there. You're 3, go over there in that corner. 4, go over there with Andres, where he's at. 5, go in the middle.
You look like you were doing this. Okay. 1, 2, 3.
So 1s, 2s, 3s, 4s, 5s. You can just move your body. You don't have to take your stuff if you don't want to. Just be careful with the camera. Yeah, go through here. Go through here. Just bring your pencil. Oh, wow. And then just have a seat, guys. When your group is ready, let me know.
Number 1. I can't do it.
1's over there, 2s, 3s, 4s are over here, and then 5s seem to be clumping up right here. All right, you guys are ready. It's a group. We have you guys work on this together. Maybe you don't know your name yet. You go get it. No? All right, you guys ready to get it, right? The group work on this together. As a group, work on this together. There you go. All right, as a group, please do not move on to problem 2 until your whole group is done with number 1.